Imagine a photograph of the deepest darkness humanity has ever seen. Not black, not empty, but filled with thousands of points of light. Each one is a galaxy, billions of stars bound together by gravity across cosmic time. Some appear white, some yellow, some orange as they burn across the void. But 6 of them glow red, impossibly red, stretched by the expansion of space itself. And when astronomers measured their distance, they found something that should not exist. Galaxies as massive as the Milky Way, fully formed, burning 500 million years after creation. According to every model we have built, the universe had not yet learned to build such things. Yet, there they are, defying explanation. 6 impossible answers to a question we never. What forced the early universe to grow giants before it learned to walk? On December 25, 2021, an Ariane 5 rocket lifted into darkness above French Guiana. Inside its payload fairing sat the most powerful telescope humanity had ever built. The James Webb Space Telescope, 6.5 meters of gold-coated beryllium mirror. Designed to see what Hubble could not, the infrared echo of the universe's first light. It traveled not to Earth orbit, but to a point 1.5 million kilometers into deep space. There, gravity from the Sun and Earth balanced perfectly. A stable point called JWST unfolded its sunshield, 5 layers thinner than human hair, stretching tennis court wide. One side faces the Sun, heating to 85 degrees Celsius in constant bombardment. The other side faces the void, cooling to minus 233 degrees in perpetual shadow. Between them, the telescope sits cold and dark, waiting to see the invisible. By June 2022, JWST began the CEERS program, Cosmic Evolution Early. The target was a patch of sky in Fornax, no bigger than a grain of sand at arm's length. Inside that window, thousands of galaxies waited, most invisible to every telescope before this. The near-infrared camera, NIR-CAM, captured light in multiple filters across hours of exposure. Photons that traveled 13 billion years across expanding space arrived one at a time. When the images downloaded to Earth, astronomers saw fields of red dots scattered everywhere. Galaxies so distant, their light had been stretched entirely into the infrared spectrum. Dr. Ivo Labbé at Swinburne University in Australia downloaded the public CEERS data. His team started measuring every red dot, analyzing brightness in different wavelength filters. This technique, photometric redshift, reveals distance by measuring how far light has stretched. The redder a galaxy appears, the farther it is. The older its light, the younger the universe was. Among thousands of candidates, 6 galaxies stood out immediately, not because they were faint, because they were impossibly bright for objects that red, that distant, that ancient. Their calculated redshifts ranged from Z equals 7.4 to Z equals 9.1 across the sample. In cosmic terms, this means light emitted 500 to 700 million years after the Big Bang. The universe at that time was less than 5% of its current 13.8 billion year age. Still an infant by any measure, still assembling its first structures from primordial gas. Finding galaxies at such distances was expected. JWST was built specifically for this purpose. But Dr. Labbé's team noticed something wrong immediately when they estimated stellar masses. Brightness translates to mass when you account for distance and the physics of starlight. The most massive of the six contained between 60 and 100 billion solar masses of stars. That is comparable to the Milky Way, a large spiral galaxy with 13 billion years of growth. These galaxies had assembled equivalent mass in under 700 million years of cosmic time. The team rechecked every calculation, tested different assumptions about dust and star formation. The masses stayed high, too high, violating every prediction from standard cosmological models. To understand why this matters, you must understand how galaxies are supposed to form. The Lambda CDM model describes a universe dominated by dark energy and cold dark matter. Structure begins with quantum fluctuations, tiny density variations stretched by cosmic inflation. These overdense regions attract matter gravitationally, dark matter first, because it only feels gravity. Gas falls into dark matter halos, cools, condenses, and eventually ignites as the first stars. This happens perhaps 100 to 200 million years after the Big Bang in the densest regions. Stars live, die, explode as supernovae, seeding new star formation in an accelerating cycle. Galaxies grow by merging with neighbors and accreting gas from their cosmic surroundings. This process is slow, regulated by stellar feedback, radiation, and winds from massive stars. Computer simulations predict first galaxies should be small, millions of solar masses, not billions. Milky Way-sized galaxies should not appear until the universe is at least 1 billion years old. Yet here were 6, fully formed, massive beyond prediction, existing impossibly early. If the measurements were correct, these 6 galaxies contained more stellar mass than predicted. Not just more than expected in those specific objects, more than should exist in that volume of space. According to Lambda CDM, there simply had not been enough time to build such massive structures. Dr. Labbé and his co-authors wrote their paper with extreme caution and appropriate uncertainty. They acknowledged photometric redshifts can be wrong, that dust can mimic high redshift colors. They noted active galactic nuclei can boost brightness without requiring massive stellar populations. But they also could not ignore what the data clearly showed across multiple independent analyses. On February 22, 2023, the paper appeared in Nature with a deliberately careful title: A Population of Red Massive Candidate Galaxies at Z greater than 5. The astronomy community reacted immediately, some with excitement, others with deep skepticism. Informal discussions began using a term that captured both reactions perfectly: universe breakers, galaxies that break our understanding of how the cosmos works. Dr. Joel Leha at Penn State ran independent analyses and confirmed the mass estimates. These objects were genuinely massive and genuinely distant, not artifacts of bad data. Dr. Erica Nelson at University of Colorado examined their morphologies in the JWST images. The galaxies appeared compact and dense, not the extended diffuse structures models predicted. Dr. Catherine Whitaker at UMass calculated required star formation rates from the masses. If these galaxies formed all their stars in 500 million years, rates must be extreme. perhaps 100 to 1,000 solar masses per year, compared to the Milky Way's current 2 per year. But there remained the possibility that the measurements themselves were fundamentally wrong. Photometric redshifts estimate distance from colors, not from precise spectroscopic measurements. Dust within galaxies absorbs blue light preferentially, making them appear redder than they are. An extremely dusty galaxy at lower redshift could perfectly mimic a dust-free galaxy at high redshift. Active supermassive black holes emit light across all wavelengths, dominating their host galaxies. Their emission can make small galaxies appear far more massive than their actual stellar content. If even half of the 6 candidates were misidentified, the crisis would diminish significantly. JWST carries a second instrument designed to resolve exactly this kind of ambiguity. NIR-SPEC, the near-infrared spectrograph, splits light into component wavelengths like a prism. Unlike cameras that measure brightness, spectrographs reveal precise redshifts directly from hydrogen and oxygen emit light at specific wavelengths determined by fundamental atomic physics. Measuring how far those lines have been stretched gives exact distance with no ambiguity. No dust confusion, no black hole contamination, just direct measurement of cosmic expansion. By late 2023, follow-up spectroscopy began targeting the 6 massive galaxy candidates. The first confirmed results arrived in December 2023, and the answer was both clarifying and 4 of the 6 galaxies received spectroscopic confirmation of their photometric redshifts. Z equals 7.6, Z equals 8.5, Z equals 9.0, and they were genuinely ancient, genuinely massive, genuinely impossible according to standard models. 2 of the 6 turned out to be misidentified, lower redshift galaxies reddened by dust and black holes. Still interesting objects, but not universe breakers, not violations of fundamental cosmology. 4 remained. 4 confirmed galaxies with ages between 500 and 650 million years after 4 galaxies with stellar masses approaching or exceeding the mass of the modern Milky Way. 4 problems for lambda CDM cosmology that spectroscopy could not make disappear. But confirmation of their existence only sharpened the central question without answering it. Not whether these galaxies exist. That question was settled definitively by spectroscopy. The question is how? What physical process could build such massive structures so quickly? Several hypotheses emerged immediately, each attempting to explain the impossible without breaking physics. The first hypothesis focused on star formation efficiency in the early universe. Perhaps early galaxies converted gas into stars far more efficiently than models assume. Instead of 10% efficiency typical in modern galaxies, perhaps 50% or even 70% efficiency. More stars from the same amount of gas means greater mass in less time. But stellar feedback, winds and radiation from massive stars naturally regulate star formation. Stars heat surrounding gas, disrupting further collapse, preventing runaway star formation. Observations of nearby galaxies consistently confirm this self-regulating limit across cosmic time. Why would the early universe operate under completely different physical rules? The second hypothesis proposed a top-heavy initial mass function in the first galaxies. The IMF describes the distribution of stellar masses when stars form from collapsing gas clouds. In the Milky Way, most stars are small, less than 1 solar mass, burning faintly for billions of years. Only a few percent are massive stars above 10 solar masses, burning bright but dying young. Massive stars are hundreds of times brighter than small stars for the same total mass. If early galaxies formed primarily massive stars, they would appear brighter without being more massive. This could explain the observations without requiring impossibly large amounts of stellar material. But massive stars die quickly, exploding as supernovae within just a few million years. If these galaxies formed only massive stars, they should fade rapidly as those stars die. Follow-up JWST observations through 2024 showed the galaxies remained bright across multiple epochs. Their light was not fading as the top-heavy IMF hypothesis predicted it should. The third hypothesis turned to dark matter, the invisible scaffolding that structures the cosmos. Perhaps dark matter halos in the early universe formed faster or larger than models predict. Larger halos pull in more gas gravitationally. More gas means more star formation. But changing dark matter properties to fix early galaxies breaks everything else in cosmology. Dark matter affects structure formation throughout all of cosmic history, not just the first billion years. It shapes the cosmic microwave background, galaxy clustering today, the large-scale structure of everything. Tweaking dark matter parameters to explain universe breakers makes other observations stop working. The fourth hypothesis suggested supermassive black holes rather than stars produced the black holes, billions of solar masses, already grown by 500 million years after the Big Bang. Their accretion disks shine intensely as matter spirals inward at relativistic speeds. This emission can mimic stellar populations in photometric observations without resolution. But growing billion solar mass black holes in 500 million years also violates standard models. Black holes grow by accreting gas and merging with other black holes. Both processes take time. Starting from stellar mass black holes at 100 million years after the Big Bang is optimistic. Reaching a billion solar masses by 500 million years requires continuous maximal accretion. Possible theoretically, but barely, pushing every parameter to its absolute physical limit. And there was a fifth possibility, one that few astronomers stated directly in published papers. Perhaps lambda CDM cosmology is incomplete. Not wrong entirely, but missing something fundamental, some physical process or force that accelerated structure formation in the first billion years. Then weakened or turned off entirely, allowing later cosmic evolution to proceed normally. We do not know what such a process would be or how it would operate. Dark energy behaving differently in early epochs before settling into its current constant value? A phase transition in dark matter properties that changed interaction strengths over time? Modified gravity at cosmological scales that standard general relativity does not predict? Speculation without observational evidence is not science. It is storytelling without constraint. But neither is ignoring observations simply because they contradict established theory. Science advances not by defending models, but by following data wherever it leads. The discovery forced JWST to continue searching deeper, and the findings only multiplied. By mid-2024, over 30 galaxies had been spectroscopically confirmed at redshifts above 7. Several showed stellar masses comparable to the original 6 universe breakers. The phenomenon was not an isolated fluke. It represented a genuine population. A population that standard lambda CDM cosmology had not predicted and could not easily explain. In July 2024, JWST discovered a galaxy at redshift 14.32, just 200. At that epoch, the universe was barely 2% of its current age, still assembling from primordial chaos. Yet this galaxy already contained several 100 million solar masses of stars burning steadily. Each new discovery pushed the boundary earlier, made the timeline tighter, sharpened the contradiction. Dr. Dan Coe at Johns Hopkins analyzed the cumulative data from all high redshift galaxy surveys. He calculated that the number density of massive galaxies in the early universe exceeded predictions. Not by a small factor that could be explained by refining model parameters slightly. By factors of 5 to 10, discrepancies too large to dismiss as observational uncertainty. Something about our understanding of the first billion years of cosmic history was deeply wrong. Dr. Michael Boylan-Kolchin at University of Texas published an analysis in August 2024. He showed that forming these galaxies required converting nearly all available baryonic matter into stars. Not 10%, not 50%, but approaching 100% efficiency. That efficiency is physically implausible given everything we understand about star formation physics. Stellar feedback should prevent such complete conversion under any realistic scenario. The theoretical community began proposing increasingly exotic solutions to resolve the tension. Primordial black holes seeding galaxy formation earlier than stellar processes could begin. Warm dark matter instead of cold dark matter, changing the collapse timescale of early structures. Modified gravity theories that strengthen gravitational attraction at specific early epochs. Each proposal solved the galaxy problem, but introduced new tensions elsewhere in the data. No single modification to lambda CDM could explain the universe breakers without breaking something else. What does this mean for our story of cosmic history, our narrative of gradual hierarchical assembly? For a century, cosmology has taught that the universe began simple and grew complex slowly. Tiny fluctuations expanded during inflation, grew over billions of years into galaxies and clusters. Small structures formed first, large structures assembled later by merging smaller ones together. This narrative is encoded in textbooks, simulated in supercomputers, taught as established science. But JWST shows the early universe was not as slow or as simple as we believed. Not as gradual, not as hierarchical, not as patient as our models assumed it must be. The first billion years were more violent, more efficient, more productive than theory predicted. And if our models fail to predict what JWST discovered in the first year of operation, what else are we missing about cosmic history that better observations will reveal? The universe does not care about our theories or our carefully constructed cosmological models. It does what fundamental physics allows, whether or not we understand the mechanisms fully. And physics, we are learning with every new JWST observation, allows more than we imagined. The universe breakers are not anomalies to be explained away with clever adjustments. They are messages from the early cosmos, telling us that our story is incomplete. That the universe grew faster, built bigger, and accomplished more in its infancy than we thought possible. What advantage did the early universe possess that later epochs lost over cosmic time? Higher densities allowing faster collapse and more efficient gravitational assembly of matter? Different physics operating when the cosmos was hotter, denser, more energetic than today? Or simply processes we have not yet discovered because we never needed them to explain anything before? The universe breakers have forced cosmology into unfamiliar territory without a clear map. We know lambda CDM works extraordinarily well for the universe from 1 billion years onward. It predicts the cosmic microwave background, galaxy clustering, supernovae distances, but the first billion years, the era JWST was built to explore, may operate differently. Physics we thought was universal may have boundaries we never tested until now. The early universe may have been a different place with different rules we are only beginning to see. When we look at the Jurassic period, we see a world dominated by giants built by high carbon dioxide. When we look at the early universe through JWST, we see galaxies built impossibly fast by unknown processes. Systems pushed to their limits find solutions that seem impossible until you observe them directly. Both are telling us the same fundamental truth about how nature operates at extremes. Brachiosaurus was not an accident. It was the mathematical result of Jurassic atmospheric conditions. The universe breakers are not anomalies. They are the mathematical result of early cosmic conditions. Conditions we do not yet understand fully, but are now observing directly for the first time. Earth does not waste its experiments. It archives them in rock for when we learn to read them. The cosmos does not waste its history. It archives it in light for when we build telescopes capable of seeing. We are what 13.8 billion years of cosmic evolution produced from primordial hydrogen and helium, and we have finally built instruments powerful enough to see where that story truly began. The universe breakers are not the end of cosmology. They are the beginning of cosmology's next chapter. A chapter where the first billion years are no longer theoretical extrapolation, but observed reality. Where models must match data rather than data being dismissed when it contradicts models. The cosmos is teaching us humility, showing us that our best theories are approximations, not absolute truth. And that is not a failure of science. That is science working exactly as it should. Thank you for staying with us until the very end of this journey through deep cosmic time. If this exploration moved you, subscribe and stay for the next chapter of discovery. Your curiosity is what keeps the universe revealing its secrets to us. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.